drive. Yeah. Anything on the desktop is cleared.
That's not what we just talked about last time with Nicholas. Okay, he said as long as maybe it's just a machine profile. All right.
Computer hates you.
I guess. Save. That was the trick. To desktop. Please enter your full name. What do they want this for? You're not going to get any from me. Come on. Who else is there? Might be somebody who didn't know where the classroom is. That's Travis. Make sure he's not out there. If somebody comes here, would you send them next door to my class?
If somebody comes in here?
Yeah.
Which class is it?
Linear statistical models. Math 483?
483 statistical models?
Yeah. If someone comes, because... Thank you. I'm sorry, I'm using this room on Monday, Wednesday, and I'm over here on Thursday. Sorry. Yeah. Why don't we have a clicker for that? These rooms are not clickerfied. Okay. Okay. I calculated studentized residuals. This was some data that I cooked up to illustrate influence in a model. And so there we had the X values, 5, 8, 1948, and so on. The scatter plot was, and the straight line fit was shown down here. It's kind of blurry, isn't it? And the residual plot over here. Okay. Residuals versus y hat. So there seemed to be a pattern in the residuals, down, up, and so on. And so it looked like the model was inadequate just from that. And what we did was we studied one particular observation, observation number 9, which had the largest HII, 0.866. This is the H matrix. Yes?
Is your y hat your predicted?
Yes. Y hat is predictive. So here's H max, 0.866 on the diagonal of the H matrix. We all learned how to compute that last time. Then we calculated the studentized residual. Let's see, how did we do that? We took the residual for number 9. What I've also asked for from Excel, the standardized residuals are roughly the residual divided by sigma hat, which is the 1.9 here. And as I said, I think these actually may be computed. I'm thinking my second guess, though I haven't checked it yet, by dividing the residual by the deleted estimate of sigma hat, which where I delete the ith observation. We can check that again. There's various things that might be done there. However, the studentized residual is defined by dividing sigma hat by, the residual by its estimate of variance of the. So I get a truly normalized thing. What I mentioned last time was that the variance of E sub I is equal to, let me put the parenthesis, the variance of E sub I, let me put this in higher font so you can read it. Well, let's try this. Variance of E sub I is equal to sigma hat squared divided by 1 minus HII. Okay? That's the variance. So the standard deviation is the square root of that. I'm sorry, it's not divided by times. Must be. Times. Okay. We did that last time. Yes, of course, because the variance covariance matrix is I minus capital H. There's no divide by here.
But this is where H is X transpose X inverse?
H is X times X transpose X inverse times X prime, the projection matrix. H, oh, I like this. The board is wider. I can actually use the board on this one. Is X prime X inverse X prime, the projection matrix, onto the column space of X. What we said was that the variance covariance matrix of the error vector, the vector of residuals, is equal to sigma squared I minus H. So if I want to get the variance of just a single residual, the variability of a single residual is since it's the variance covariance matrix, the variances will be in the diagonal, and I take the corresponding diagonal element of this matrix. So the diagonal element of this matrix is sigma squared times 1 minus HII. And so the variance is sigma squared times 1 minus HII. Therefore, the standard error of EI, we could write it therefore, this is using all our statistical language. Standard error, come on, let's give you some more font space. Standard error of EI, therefore, is equal to sigma hat. You replace sigma by sigma hat, and then you have the square root of 1 minus HII. Oh boy, I better put a times sign there. Okay? And that's what we divide the residual by. Here it is in this formula. I take AC13, AC13 doesn't exist. Oh yeah, here it is. Sorry. AC13 minus 1.199, okay? And divided by this sigma hat and the square root of 1 minus HII. All right? So we've done that. And that's the studentized residual. So it's going to be convenient for you to somehow come up with a diagonal of the H matrix. You may have to do that by hand. You may have to compute the H matrix and then pull those diagonal elements off by hand. Copy and paste them. And it's kind of a nuisance. If you want, since you got to get all the studentized residuals.
The thing you had in your Maple worksheet, you had it done at...
I had it done in Maple. That's fine because I can do all kinds of matrix manipulations. I have all the matrix elements referenced, all right, automatically. Here the matrix elements are not referenced automatically to my knowledge in Excel. You might spend 5 minutes if you're on an Excel website to see if you can find matrix manipulations or something. I don't know. I'll check it at the break a little bit, but maybe on a different computer because this one, I don't like the search function on this particular Microsoft Professional. It's too slow. Then I took the R student. What's the difference? R student is defined by, you do indeed, this is called RI, by the way. So RI is therefore EI divided by sigma hat and the square root of 1 minus HII. That's the definition of the studentized residual. The difference is now with the R student, it's more calculation intensive. But R student is defined by TI equals EI divided by not by sigma hat but by S sub I, square root of 1 minus HII. You replace the sigma hat by the estimate of the standard deviation when the ith element is deleted from the analysis. Let me double check this formula. Pretty sure that's right. Yes, so that's called T9. So what I have for T9 is that I have to move all the way over here. So I have T9 is minus 1.199 divided by, okay, what I'm calling the square root of 2.92 times 1 minus 0.866. So this is your 1 minus HII. This is your SI squared under here, square root sign, and this is your EI up here. Okay? There's a formula for SI squared, which is convenient, because I don't want to have to go through the calculation every time. And the formula is SS res, okay, minus EI squared over 1 minus HII. Okay, you take the total error sum of squares, you subtract off the contribution to the error sum of squares contributed by the ith residual, except divided by this factor 1 minus HII. Okay, and then you divide by the number of degrees of freedom that would be left. You take 1 degree of freedom away. You divide SS res by n minus p, so this would be n minus p minus 1. Okay. So in my particular application, my SS res was 37.04. My EI squared was the 1.199 squared. 1 minus HI was 1 minus 0.866. Then I divided, instead of, let's see, how many degrees of freedom were there for error? There were 10 degrees of freedom for error. Okay, so instead of dividing by 10, I divide by 9 because I took one of the squares, error squares out. So it's about as nice a formula as you can have. And I don't have to recalculate I don't have to do the whole analysis of variance again with the ith element removed. Okay? So that's kind of nice. I did have to have the HII, of course. So I had to have the H matrix. But then I can do this for any observation. All right? Once I have the HII column that you're going to produce for your problem. Okay? So that comes out to be a little bit bigger, 1.915. How would you interpret them? Well, they measure influence through how remote the data point is in X space, basically. The larger HII, the more remote the regressor vector is in X space. Okay, so that's being taken into account, the remoteness of the regressor.
If it's larger, does it mean that it's further away?
It means that the data point is remote in X space, okay, or the residual is just large, okay? So it's either indicating either an outlier or an influential point. If these residuals are large, okay? By deleting the point, you accentuate the effect of the size of the residual, obviously, and well, not only that, but also the influence. So it's just bumping up the studentized residual a little bit. It's just okay. Then I've actually thrown in another number, which we're going to only supposedly construct when we get to Chapter 6, which is another proposed measure of influence. Okay. But he's not asking about that here. What does the author say about the interpretation of our student? There's something in there, too. You can read up in the book. Okay? He's got some stuff in there. Other residual, okay. Residual plots. Just before that, here it is. He's got the studentized residuals, blah, blah, blah. Methods of scaling residuals. Okay. Since HII is, bottom of page 133, since HII is a measure of the location, the variance of EI depends on where the point XI lies. Okay. Violations of model assumptions are more likely at remote points, and these violations may be hard to detect from respect to the ordinary residuals. Therefore, you go to the studentized residuals. Okay. So we're not going to say there's really a problem until, at least according to these residuals, until you get something 3 or 4 in magnitude. But then we calculated this one. There's an extra F, by the way. It's only D. It's not really having that big of a fit. It's okay. There's only 2 F's in here. DF fits. We could look that up in Chapter 6 to see what they're talking about. Chapter 6, because there's another measure. Okay. We also, on page 214, when we also investigate the deletion influence of the ice observation on the predicted or fitted value. This leads to a second diagnostic proposed by 3 authors. And let me assist. So not only do you this number is the number of standard deviations at the fitted value yi hat changes if observation yi is removed. Okay, so you have something called, this is how it goes. So the fitted value just changes a lot. All right, so that's why the fit, df fits sub I equals yi hat minus y delete I. But you can still calculate yi hat by putting the regressor back in. You recalculate the regression coefficients, all right, with the ith observation removed. And you also then accordingly you're going to use this. You're going to use the SI instead of the sigma hat because you're going to delete that observation. And then there's a HI here, HII. There's a different formula for the variance of yi hat minus the deleted y hat. So this comes out. So if I deleted observation 9. The actual regression line would change, right? And so the fit, you can see that if you want. I can delete observation 9 and we can see where the regression line goes. All right? So that's a different kind of a business. Observation 9 was just 4175, so I have to copy this over. This is the long way, where you actually recalculate doing it this way. Get off of there. Okay, there's the data. So now if I go to data analysis, I have to change the computer too. Wouldn't you know? First time in the room. Data analysis. Regression, okay. You can put range. The y's are here. The x is over here. And I just want output range, and I also want I want the line fit plot. That's what I want. Okay, so let's get this line fit plot over here. Okay, let's drag it down over here. Compare it. Actually, I should have gotten the predicted values too.
Well, why don't you just click on the line and add a trend line, and it'll tell you exactly what the equation is.
Okay, add trend line?
Yeah.
Cool.
You want linear, go to options.
Options, nice.
And you can, display equation on the chart. It's this box down at the bottom of the page.
Display equation on chart. Okay.
I'll do that for the other one too.
Okay, that's good. Didn't do it.
Yeah, you have to click on the data set.
Oh, you have to click on the data set?
You have to click on a point.
8 point.
Yeah.
Well, that's good.
Options.
So we could do everything options. Okay. Excellent.
So now Now you can see the different
Okay.
slopes and intercepts.
Slopes, okay. So the slope, the slope changed by quite a bit. Okay, not 50, not that, but it did change by quite a bit. Okay, so now the predicted value at 40. Now, 40 is not on the x-axis here, right? It's not on the x-axis here because it wasn't in the data, but I can pretend that it was. So where's this line going to end up if I put in 40? Okay. If I put in 40, I'm going to get 40 times 0.6, which is 24, plus 2.4, which is 26, right? 26 and a half. Whereas on the other one, the predicted value, what was the predicted value? I didn't show it. But, okay, I'd have to calculate it. The other one, 26 versus if I put 40 in here, even though the intercept is a little bit bigger, that's going to be way less. Okay? That's only going to be 40 times 0.35, which is 14. Plus 4 is 18. So there's a difference of 8. Okay? So basically, 8 divided by 2. And then there's a 0.866 here. So you're getting something over 4. All right? I'm sorry, was there a square root there? There's a square root here. I'm sorry. But that's still just closer to 1. So that doesn't really do much if you're remote in the X space already. The HII doesn't do hardly anything. It just brings it up a little bit. The main thing is this divided by your sigma. Okay? So SI is still about 2. All right, let's say. A little bit bigger maybe. A little bit smaller, I mean. Anyway, it's not much changed. Okay. This was the square root of 2.92 was my SI. All right, so SI here was the square root of 2.92. Now I could actually check that if I wanted to. What is? I could check my hypothesis that these standardized residuals are just divided by SI. Let's take the 1.19. Okay. I have a feeling it's still not right. Divide by the square root of 2.92. Let's just see. I get 0.7. Let's widen it up a little bit. Nope, that's not right. Okay. So that's not what the standardized residual is either. So I'm not sure. Okay. What that is in Excel.
That's not the standardized residual that they have here?
No, it is not. I don't believe so. Let's divide by the 1.925. Okay. So somewhere between where I delete the observation, where I don't delete the observation. I'm not sure what it is.
Where did you get 1.925?
That's sigma hat.
Okay.
The version of S, capital S. That's just basically your S.
Okay, cool.
Okay.
I wasn't seeing it. So.
Okay. All right, does that explain it? What's the interpretation? You have to dig into that just a little bit. I'm going to make you do that. Otherwise, you do the problem. You have to do the calculations and you have to do the interpretation. All right? You'll get some large ones. Okay? You can check to see whether you're remote in X space or not. If you're remote in X space and it's large, then okay, you basically say this is an influential observation. If you're not remote in X space and it's large, then you say, okay, you have an outlier. That means the standardized residual already would have been big. Okay? That's roughly how it's going to go. The word outlier gets kind of mushed around, but that's how we're going to look at it. You could also have a very large residual for a point remote in X space, but that seems unlikely. Okay, now we could have a look at how you treat outliers, which is the new lecture for today. If you look at the very first example on the rocket propellant data. Here's a situation shown on page 17 of your text. There's the scatter plot of the rocket propellant data. And can you identify without even looking at the residuals if there are a couple points that look a little bit different on that page? Which points? 6 and 2200 and 19 and 18 and 1700 or something. Yes, that is correct. These 2 points down here. Okay. Well, it turns out the straight line goes through here, obviously, and you just have 2 points sitting down below it. Okay, as if on a line parallel to that straight line. What that means is that if I take those 2 points up, those turns out they both have large negative residuals, so they would be considered outliers. All right. Now, suppose I take those, and you can read in the text about that. Okay. If I take these 2 out and reanalyze, turns out then it's not going to change the slope or the intercept of this line hardly at all, at least especially the slope. Okay. It might change the intercept a little bit. Okay. Because it was trying to meet those points by not making too big of residuals, so the intercept would have been down here a little bit lower with them in. Okay? With them out, the intercept's going to be a little bit higher. Okay, but the slope is almost unchanged. So the estimate of the parameter is unchanged.
Well, the estimate of that one parameter.
Beta 1 hat, yeah. Okay? Beta 0 hat, I guess, maybe changed a little bit. Okay? The standard error of beta 1 hat will have been reduced if I take those 2 points out, because there's less variability in the model now. Okay? So the estimate of sigma hat squared went down, right? Which seems good, right? It's a good properties to have. However, there's really no influence on the model by those 2 points, right? Because the estimate of beta 1 hat didn't change. So what are you going to do? Is it realistic to just take them away? The author says no. Basically, you don't take outliers away. You just note them and then try to get information out of them. Okay?
Actually, that might be where you want to be.
It had to do with the shear strength of this rock repellent data. I don't know. I mean, I have no idea what that would apply to. But in other words, it looks like there's just maybe more variability than you thought. Okay, the sigma squared is really bigger than you would want it to be, but that's just the way it is. Okay. Perhaps these were some different propellant data that came off a different shelf or something that somebody had moved into the storeroom. Who knows from when? Okay. You may have no way of knowing. Okay, if there are large residuals, then you can figure out, oh, okay, somebody put the decimal point in the wrong place, or I copied it wrong, and so on. You can investigate such problems. You do that yourself when you copy data down. It happens all the time. So you first investigate and see if anything like that. Okay. Or it might just be a mixture of 2 populations of propellant. Okay, we don't really know. Okay. So there's nothing you can do about it. Basically, is the conclusion. Okay. But you sort of check it out. Now, since this is a simple linear regression problem, all is well because you can see the scatter plot in 2 dimensions. You can see visually whether the points are remote in X space and just what's going on exactly, practically. And you can't do that if you have a higher dimensional problem.
So in this case, it's really not remote in X space at all.
Not that much.
I mean, both those points.
Yeah, I mean, you could actually calculate the HIIs. Yeah. Then they're within range,
Well, wouldn't X space just be the X-axis?
Well, yeah, but you'd still be remote. You have to near the end of the endpoints of the interval. Okay, then they can have more influence. Okay, or if there was one way down here, I mean, there was a big gap or something. But there is nothing like that. So the HIIs here are not that big. Okay. All right. So you plot the residuals. You calculate R student and the studentized residuals. Later you might calculate it as D fits. Okay? And you also plot the residuals versus time if appropriate. Okay? See if there's any kind of autocorrelation. What is that? Let me explain that picture a little bit. There's not a whole lot of explanation required, but the picture is on page 146. If time is a factor, which they do give you in one of your problems for next week. Okay, they give you the time in problem 4.9, I believe. They want you to plot the residuals versus time. These are idealized, prototypical examples when there are autocorrelations. That is, when the residuals are correlated, okay, positively. Let's say E1, the correlation between E1 and E2 is positive, the correlation between E2 and E3 is positive, the correlation between E3 and E4 is positive, the correlation between E4 and E5 is positive, that type of thing. Neighboring residuals, let's say according to time. Right? So E1 was the first residual in time, E2 was the second residual in time. If those are correlated, then they tend to, when one is large, the other one tends to be large, positive. The other one tends to be positive. Okay? So the residuals might go up, but then when one is negative, the other one might tend to be negative. So then they would match. Okay? They would match along, and so applying the residuals versus time, you might get something like the first graph. If the correlation is negative, then they tend to switch signs. So when you get like a deterministic up and down, too much up and down. Okay? And I suppose that there would be statistical tests accordingly, and there's not going to be anything here for that. Okay? But there's too much up and down and too little up and down. Okay? That's basically what's going on there in those two pictures. If you can get that. Okay. Something we didn't cover last time was the partial regression plots. I believe you were asked to do those too. One of your problems next week. Are you not? 4.4. What's a partial regression plot? I mentioned it last time, but how would you actually do it? Construct and interpret the partial regression plots. Okay.
Can you just use the existing data and then plot versus x1 or x2 or whatever one you're calling it?
Let's see. There is a formula for what you're supposed to do. Where are my notes? This thing is in the way. Okay, that's correct. Useful for considering whether add in a variable to a given model after other variables are already in the model. So it's a question of whether should I add another variable in. A visual inspection. Okay, here's the method. Right. In adding, let's just consider adding x2, a second regressor, after x1. Okay. We would first fit x1 and compute. There's kind of a lot of notation here, but it's not too bad. You're going to calculate y hat x1 equals gamma 0 plus gamma 0 hat plus gamma 1 hat x1. He calls it theta 0 hat plus theta 1 hat x1. Okay. Since you hadn't seen it theta yet, I used gamma. Okay. All right. So this is the simple linear regression fit using just variable x1. He calls it y hat of x1 because you only have x1 in the model. Okay? Instead of y hat, because y hat corresponds to the prediction of the full model in our usual notation. Okay. So now you're going to have EI of y given that you fit x1. That's the residual. Correspondingly is simply yi minus this y hat of x1. Okay? Yeah. Some y hats. must have been left off. Okay? In my notes. Okay. Looks like a y hat. Now, what are we going to do? We're going to regress x2 on x1 and find the following. Okay. And you obtain that x, just with a simple linear regression, xi2 of x1. So you're going to do the similar thing. Equals alpha 0 hat plus alpha 1 hat xi1. So I'm going to treat x2 as I treated y. It's going to be like a second y. I don't have to put this I here if you don't want. Okay? But there's the simple linear regression of x2 on x1. There's the predicted equation, okay? And then I could calculate then another residual, E hat sub I, x2 given x1, okay, equals xi2 minus x hat sub I of x1, okay? So it's a lot of notation, okay? So basically I just take the residuals from fitting x2 on x1. Okay, it's simply. So you have, in other words, if mechanically with Excel, you're going to say, all right, just simply an regression of y and x1, calculate the residuals. That's this. Okay? Do simply an regression of x2 on x1, calculate the residuals. That's this column. Now plot the one set of residuals against the other set of residuals. Trivial, right? Okay. y given x1 versus I don't know why I put the hat on here. It shouldn't have been hat. Versus x2 given x1. Okay? Where this is on the vertical axis, and this is on the horizontal axis. Okay? So it's really quite simple. You have, the way you would set this up is you'd have x1 variable, and you'd have y1 variable. You could also write down the x2 variable and the y2 variable and just do, well, it doesn't really matter since you have x1, x2, and y. Okay? You would regress y and x1, regress y and x2. Only one column of x is in your regression tool. Okay? You would calculate the residuals for each. Okay? Residuals, so then we call these y given x1, and then you have x2 given x1. And so then you would calculate the residuals from the regression of y on x1, you calculate the residuals from the regression of x2 on x1. Okay? And then you just, this is the, I guess I want to have them interchanged if you want to get this set up right, because it's x and then y on your xy scatter plot. So I should put it this way. I should do the x2 on x1 first if I'm using Excel. Okay, whatever. You just get the column residuals. You're going to have to move them, cut and paste them anyway. Okay, so it's going to come out in these outputs. Okay? Then you just do the scatter plot of these two columns. Okay. There's the partial regression plot. What should it look like? If x2 contributes to the model, the claim is this partial regression plot should actually be a straight line to the origin with slope approximately beta 2. Okay? Roughly speaking. And the argument for partial regression plot, why is that? So I thought I would try to argue why that is the case. mathematically. Okay, let's see if we can argue it. In the first case, I'd have y equals gamma 0 plus gamma 1 x1 plus e y given x1. That's the definition of the e. Okay? And of course, this might not actually just be error. It might not just be random error between minus, sigma and sigma or what have you. It's going to have some trend in it, assuming that x2 does contribute to the model. Okay? Now, what is that? Now also have x2 is equal to alpha 0 plus alpha 1 x1 plus ex2 given x1 by definition. Okay? So, what do I have? I have y, but now I rewrite y. Y is beta 0 in the true model plus beta 1 x1 plus, or in the full, what I'm calling the full model here, plus beta 2 x2 plus epsilon equals beta 0 plus beta 1 x1. Now I'm going to plug in what x2 is from the second equation, plus beta 2. x2, according to the second equation, is alpha 0 plus alpha 1 x1 plus ex2 given x1. Okay? And then plus an epsilon here. Okay. Now combine terms, and you get that this is equal to, now you match terms. So now you take this first equation and the second equation right here, and you match them up. This is y and this is y. Okay? So what do you get? You get that what I have to do is this is all in terms of x1. So I get a beta 0 plus beta 2 alpha 0, beta 1 plus beta 2 alpha 1 x1. Okay? So I get a beta 2 times this plus error is equal to this. Okay? Because all this other stuff, the beta 0 and the alpha 0, should become the gamma 0 and the gamma 1. Right? So I should get that beta 0 plus beta 2 alpha 0 should equal to gamma 0. I should get the gamma 1, and I should get that beta 1 plus alpha 1 beta 2 is equal to gamma 1. All right? Just matching the coefficients of the linear terms. And then I should get this ey given x1 should equal, therefore, beta 2 times e x2 given x1 plus epsilon. Okay? All right. So with that little bit of magic, then you see, yes, indeed, the slope of the ey given x1 should be beta 2. Yes?
So then do you just do your test to test whether when you plot the e of x2, x1 versus y versus x1?
Yeah.
You just test that with your, how you would normally test to see if the slope is 0?
Yeah, you could. You could.
Normal?
You could. You could do that. You could do that. Have play with that. Sure.
Okay.
The intercept should be 0. Okay, in this. You would expect the intercept to be
0?
Well, it should be close to 0, yeah. That's what I'm getting. I'm getting an intercept 0 here. There's no intercept now, according to this calculation. Anyway, yeah, you can play with it if you want. You don't have to. You just have to plot them, okay, and look at it. All right. See if visually it looks like there's some slope there. Okay.
So if it's just a really small number and you're not sure, then you test it. But most of the time you can just say,
this is a visual technique. This is a visual technique. It's not a. It's using, maybe you don't know, but it's using the mind's visual operating system, okay, to help with statistics. That's the whole advent of computers and so on in the modern age for statistics, to actually use the visualization of residuals and so on to help figure things out. So that's all you're being asked to do then. Questions more about that? Okay. Treatment of outliers, questions about that? treatment of outliers, basically the story is investigate. See what happens when you pull the observations out that seem to be doing something, and see if you can figure out more about the model. Just work around it. Don't throw it away. Okay. The moral of the story is there might be a lot of information in those outliers. Okay. All right. Let's talk a little bit about normal probability plots. You're also going to have to do those, right? Okay. What's a normal probability plot? Let's pull the screen back up. Okay. All right, so let's have a look at this. What am I doing? Can I turn the screen back on? Okay, sorry. No wonder you can't say anything. Okay. Didn't work on yet. All right. Please, screen, come. 2. Help us. Here. What I've done here is I took a sample. To illustrate normal probability plot, I just took a normal sample, generated sample size 100 of normal variables with mean 5. That's the 5. Here, can you read that? Normal probability plot for 100 independent values from n5, 2 squared. That means the variance is 4, the standard deviation is 2. You could do that with Excel, random number generation. Remember that business?
Yep.
Okay, good. What I do now is I sort those normal values. So here they are sorted. Okay? The smallest one being 0.46. Okay? I guess that makes sense. All right, you can see here the smallest value. And now what am I plotting on the vertical axis? So those are the ordered values. That's the horizontal axis. And on the vertical axis, okay, I'm saying a standard normal quantile. What is that? Standard normal quantile of j over n plus 1, where n is 100. So, okay. What's the idea? What's the definition of a quantile or a percentile? Quantile and percentile have the same meaning. What's the 1% percentile? Okay? What's the 1% percentile of a distribution? With cumulative distribution function CDF, capital F of X. All right. Capital F of X is the probability that capital X is less than or equal to X. So it's the percentage of the population under consideration, population values, ages. Let's say, for example, ages that are less than or equal to X. The percentage of people who are less than or equal to 40 years old. All right, is a certain percentage. Okay, probability, right? Probability a person picked at random from the population is less than or equal to 40 years old is just this percentage or probability, cumulative percentage. So what's the 1% percentile? It's a value of X and we'll assume that X is a continuous random variable, so age goes continuously. Right? So we can talk about somebody aged 7.3 years. Okay? All right? 1% percentile equals value of X such that The percentage of people who have ages less than or equal to that is 1%. Probability that capital X, value of X naught, such that, or I could call it X 0.01, such that probability X less or equal to X of 0.01 equals 0.01. All right? So find an age where just 1% of the population has age less than that. All right? That's called the 1% percentile. The 99% percentile, 99% of the population have age less than that, etc. 50% percentile is the median. 50% of the population has age less than that, 50% has age more than that. Okay? Any questions about that? You have the first quartile and the third quartile, the 25th percentile, 75th percentile, those kind of things. Show up. All right. So what should be a straight line is if I order the data, all right, and plot against the percentiles, corresponding percentiles. I have 100 data points, so I should plot against roughly the 1% percentile, the 2% percentile, up to the 100% percentile. And there's a little trouble there because the 100% percentile is infinity, the 0% percentile is minus infinity. So to correct for that, I'll replace 100 by 101, and I'll look at 1 over 101, 2 over 101, 3 over 101 for n equals 100, and I'll look at the corresponding percentiles there. So I'll just adjust a little bit. And so I'm going to take the percentile for 1 over 100, the standard normal percentile. So now I'm going to work with capital F equals capital phi. So let me write that over here, since I'm running out of room there. Excuse me while I move over here. So I'm going to take capital F equals capital phi equals standard normal cumulative distribution function. Okay? So how do you actually calculate the percentile? You actually just take phi inverse of 1 over 101. So I have 1 over 101, 2 over 101, 3 over 101, etc., up to 100 over 101 are going to be the fractions or percentages. Okay, the percentiles will be phi inverse of 1 over 101 is 0.0099. Excuse me, that's not correct. It's minus 2.33. That's the actual. About 1% of normal populations, of a standard normal population, has values of below negative 2.33. Does that seem about right? You can figure that out by looking up z sub 0.005 in the back of the book. Okay? It should be 2.33. I'm sorry. Z.01, yeah, is 2.33, right? Equals negative 2, because that's one tail. The Z.01 is, okay, there's negative Z.01. Okay? So in fact, this is exactly the same notation, right? Z.01. Except that they put the negative sign because Z.01 was the plus 2.33. Okay? So same exact notation that I had here. Okay? Actually, there's not 101, 101, 0.0099. Okay, 0.0099 if you like. Okay? Instead of 0.01. All right? Because that's the actual percentage here. It's 0.099. Phi inverse of 2 over 101 equals negative 2.05, which equals negative Z.0198. Okay. In our notation of percentage points. Percentage points are also percentiles, appropriately interpreted. Okay? etc. Okay, so actually the way I calculated that was, that was the formula here. Norm S inverse. S stands for standard normal. So this is the of J over N plus 1. J ran from, so I'm just calculating the norm's inverse of that first column entry. I can show you the formula. But going here, this was what? Equals norm S inverse of A4. So I'm taking the standard normal cumulative distribution function inverse of 0.0099, etc. So I just pull down that formula, and I get that column of numbers. Then I just plot those on the vertical axis and these on the horizontal axis. So all I have to do is a little bit of calculation, and I get my probability plot. Okay? And there it is. It looks like a straight line. Okay? I also calculated here the correlation between, see how straight that line is. The correlation is 0.99. Go ahead, Shane.
And your ordered values that were these random, that's just our residuals?
You're going to use your residuals in place of those. Right. So you're going to do a residual normal probability plot.
Cool.
Normal probability plot for the residuals. Now, the author says something, well, instead of doing the standard normal quantile on the vertical axis, just put percent on the vertical axis. Okay. And that changes things a little bit. It turns it into this curve right here. All right? That's the shortcut method. So it'll change an actual straight line into something that looks like the S. Okay. If it actually really was normal data. But it still kind of looks like a straight line, I guess. Just a little curve at the end. So I don't really go with the shortcut method. I think that's kind of silly. Okay. If you actually do go with percentages, then you get something called the uniform probability plot, which I showed in your notes. Okay. That a uniform variable would plot as a straight line. Okay. So you really want a uniform? Okay. So if I take uniform 0, 1 random variables and I plot percentage on the vertical axis, then I get a straight line. See what I'm saying? Because the cumulative distribution function of the uniform random variable is just a straight linear function. So what's happening? Why is it curving down and like this? Because you see there's a nonlinear stretching, okay, of the vertical axis here, as you saw in that other web page. Okay, so there's no stretching on this vertical axis, so it's taking the curve and it's like stopping it from stretching out. In this SK, right here, you can see the stretching out because there's big gaps here in the dots on the left. I'm pointing at the wrong thing. You can see the stretching here. Okay, here there's no stretching, so it's like pushed back in. Okay, instead of stretching out. Okay. So this is the shortcut method. I wouldn't use it. Okay, just don't bother if you're going to go ahead the trouble of actually making one of these plots. Excel doesn't do anything. Excel, somewhat bizarrely, in the regression tool, just takes the original y values and does the shortcut method for the ordered y values. But the y values, what are they good for? Okay? I don't get it. Anyway. Somebody will have to explain that to me, whoever wrote that. Okay. Okay. So, look at it. Maybe you could come up with some explanation. I just haven't been able to figure it out. Okay. Look at Excel's normal probability plot, if you would. Just as a favor to me. Okay, this is it. And then there's also on the, let's see, I didn't put the uniform probability plot pages on the website, but they are in your notes. Okay.
That's for the uniform?
Well, yeah, I just wanted to see what, if I actually did this shortcut method, and I put some uniforms in here, I get this picture again. Okay.
Even if you do it correctly with the uniform.
What do we do with the uniform? Okay, uniform has light tails. Has light tails, right? Let's put some uniforms in. Okay? I don't have to change just about anything, right? I'm actually, I need to introduce the random variables. I need an extra column here. Okay, and I want a column of uniforms right here, and I want to sort them. And well, that won't mess anything up because these other columns are already sorted, right? So let's just go ahead. Uniform 0, 1. Okay. So we should predict what's going to happen here, but let's just see. Tools, data analysis. I need random number generation. There it is, right there. Okay? Number of variables 1. There's only one column. Number of random numbers 100. Distribution uniform 0 and 1. Let's say, right? For the endpoints. Output range. Let's put it right here. Okay. Now I just need to sort them. A to Z is smallest to largest, I assume. Following the next selection. It's not going to affect anything because those are already ordered.
So click continue. Don't expand the selection.
What?
Click continue.
Oh, continue with this current selection.
Yeah.
Oh, I see what you're saying. That really gets you out of the ballpark. It wouldn't have mattered, though, in this case. Does everybody see that?
Well, it would have expanded it to all the way.
Yeah, but all of them are already sorted. Oh, I see. It would have messed them all up.
Sorted all your other
Oh, resorted them all. That's not good. All right. It wouldn't have changed the graph, though, because they would have been sorted together. Okay. So here we go. There's the smallest to the largest. Okay. Now, with the uniform probability plot, well, let's say so now I need to introduce this against norm S inverse, right?
Yeah.
So I need to insert another column. I guess you would have done it here.
Well, you can just use that same column, can't you? Just plot.
Let's just insert another column here. I don't understand what you mean, so I'm just going to copy this one over. Paste special, I want all the values. Okay? Now I want to chart this business, right? So what does a uniform variable look like on a normal probability plot? That's your question.
Yeah.
Okay, let's have a look. Okay, so the x-axis was ordered U 0, 1 values. Okay, y-axis was z-scores. Is a simplest version of the y-axis. Okay? I didn't put a title. That's all right. It's obvious you didn't finish. Okay? Well, just bring it down here. Well, somewhere. How about in there? Okay? Just read it a little bit. Clean it up a little bit. I always change the background to white in case I'm going to print. Just an old habit. Okay? So anyway, that's close enough, right?
So there's a pretty fine line. Like, if you got data that looked like this, would you have continued? Would you have, like, said...
So this is a normal probability plot. So what is this? Is this light tails or heavy tails? It's light tails. Let's make sure that this matches what the author said was light tails. That is very confusing. Depending on what you put on which axis, it changes. Okay? So he says B is light tailed. I got it set up so that it would match what he did. Okay? So as long as you put the z-scores on the vertical axis, okay, then you get this picture is that the documentation according to this is correct. All right, on page 139. That is the light tails. B on page 139. Light tail distribution. Let's see if we make sense out of this. The z-score is stretching the vertical axis. If I had taken just percentages on the vertical axis, it would have been unstretched. Okay, so this stretching would not have occurred. It just would have been a straight line, as you'll see on your other document. Okay, and your notes. Right? So this stretching down like this corresponds to a light tail. That's the easiest explanation. Just study the uniform, which obviously has light tails. It has no tails at all. Okay? It's flat. All right. So there's normal probability plots for you. Okay, so study them. So they're useful. In fact, on the other example, I was studying correlations. What you do is you look at the correlation coefficient. Here we got 0.992 or something like that. If the correlation coefficient is small, okay, the smaller, the less linear it looks, the smaller the correlation coefficient you're going to get, then you reject the null hypothesis that the distribution is normal. Okay, so that there is actually there are tests, statistical tests for testing normality by calculating the correlation coefficient. There are tables. What they do is they simulated tables, okay, for what the correlation should be. They do a whole bunch of samples of size 100 of a normal, okay, and they look at all the correlations, look at the distribution of the correlation, then calculate the critical value for the correlation. All right? They say, okay, the correlations are 0.992, 0.993, 0.991, 0.989, and so on. Then they find where, there's only 5% of the correlations are smaller than that, and that's the critical correlation. All right? And so they actually construct this test by simulation. That's the way statisticians can do it. Okay? So then they publish the tables. It's not done in this book because it's really not a discussion about normal probability plots. In other discussions, you might really want to know whether the variable is normal or not. Okay, here you can argue that the residuals are not going to be normal anyway, but are they anywhere in the ballpark? So they use the shortcut version even if they want. Okay, they don't really care if there's a little distension at the ends. Okay, they just want to know if there's a big outlier running around. Okay, so anyway, they exist. But I thought I would just go ahead and give you normal probability plots anyway. All right. Comments? Questions? Yes?
This refers to what we did earlier with the partial regressors.
Yeah.
So, for example, with the car data where we were plotting versus the engine size.
Yes.
And the,
yes.
That's what we would have used to say that, we didn't really need to add x2 as a regressor?
You may or may not. Yeah, you may be able to see that you didn't need to add it.
Okay. Like that would have been.
With the delivery time data, the second regressor I did notice was added, and they do argue that you did need to add the second regressor. Okay, with the delivery time data. But I think with the automobile gas mileage information, you'll see that you really don't need to. But
okay.
But it's kind of marginal whether you do or you don't. You can study the adjusted R-square. That's another way to determine whether you add in this extra variable, because the adjusted R-square will only increase when you add some variables to the model. Add some variables to the model. That's correct. The adjusted R-square will only increase if the mean square for error decreases. All right. So that's kind of useful sometimes in studying whether you want to add a variable to a model or not. So you're going to get multiple measures of quality, and they should be consistent. Some ways, and then it's a question of, well, do you really need to or not? If you already had 15 variables in the model and you saw R-squared adjust didn't really go down, and the partial regression plot looked crummy and all that, didn't have a slope or anything, you would just say, forget it. I don't need that. Okay. If you only have one variable in the model and you can afford a second one or a third one, then it's okay. But that might not be the right one. Remember carburetor barrels. I say, well, that's kind of interesting, but not so interesting. Put something else, like the size of your tires or something.
Weight of car.
Okay. All right. Yeah, weight of the car, anything. Yeah. All right, let's go on. What I want to discuss next is, I think we're also, let's see, did I have anything else left in the old notes? Besides that, methods for studying residuals. It's starting to turn into a little bit of a cookbook here, but for studying residuals, that's what you need to do. The press residual is one other kind of residual. I didn't mention too much about them. The press statistic. So that was another thing. What is the press statistic? The normalized press residual is exactly equal to the studentized residual. So I didn't talk about the normalized press residual, but if you want to talk about the press residuals in terms of defining the press error sum, the predictor error sum of squares. That's what press is. So press stands for predictor error sum of squares. Somebody made up the acronym. I guess so they could publish a nice paper. Okay. With an acronym on it. Okay. So press is defined to be equal to summation E deleted I squared. Okay, so it's not the sum of the residual squared, but the sum of the deleted residual square. Okay, where is E sub I? E sub I is equal to yi minus y hat sub I. So I take out the ith observation, calculate the regression coefficients. Alright? So the regression coefficients have changed because I've taken the ith observation out. Sometimes they change dramatically. As you saw in the modified Anscombe data that I had up there, where I got a straight line that had slope 0.6 instead of 0.36. Okay? But take out an observation, then I just go ahead and recalculate. And so then I would actually find the predicted value at that removed observation. I can obviously still put the x equals 40 back in, all right, and calculate the prediction. All right, so then I go ahead and so this is the what the residual would have been if I would have deleted that. Okay, that point, and then estimate it back in. So that is actually a big number, right? In our one case. All right. So you take this and let's see. Do I have that right? It can be shown that this is equal to EI. It can be shown. This is equal to EI over 1 minus HII. So you don't have to recalculate each time as long as you calculate that H matrix and take its diagonal. So again, that's the press. Residual, we could call it. Then you take the sum of squares of those for the press statistic. And then you can talk about, let's see, what is the R square value? R square is always, R square in the ordinary multiple regression model is SSR divided by SST. That's what the R square is. It's the square of the correlation coefficient in case of simple linear regression only. Some of you have seen that relationship by playing around with your ANOVA tables. This is equal to 1 minus SS res over SST by the fundamental relationship that SS res plus SSR is equal to SST. Okay, so you have this alternative formula for R squared. And now what I'm going to do is replace SS res by this press error sum of squares, right? Because that's the analog. So now R squared predictor is equal to 1 minus press over SST. Okay. All right. So this is kind of let's see how I believe that this R squared would have been. Let's see what happens. Okay. So this is kind of measuring how well the model predicts. In an average sense. And according to the delivery time data, when I added another variable, so you can consider this by adding another variable. When you add another variable, R squared went up. Okay, a lot. Okay, so that was another evidence that adding the second variable in the delivery time data was a good thing. Okay, so that's the press statistic. I'll read about it. I'm going to make you do some of the text reading, okay? All right. So there's all these ideas that people have come up with for trying to figure out how to, get some numbers to show whether a model predicts well, whether there's influence of a data point, whether there's a big outlier, you name it. Okay. And so there's a lot of little games out there, a lot of little numerical devices. This is one of them. Okay. Also, there's one other picture in the book that I wanted to talk about before we go on, and that is when you actually plot the residuals versus the predicted value. Okay. Page 142. If the model is adequate, you expect the picture in the upper left-hand corner. Just an amorphous blob of residuals where there's not, where the band of residuals pretty much is constant in terms of its height from left to right. There may be a little bit of tailing off because he's only got a few points on the left or right. Okay? So you may not be able to tell. But if there's a clear double bow shape like there is in part and in the frame below, then what you're seeing is the variance apparently is not constant. All right. If it's just due to a little bit of a sparsity of points on the left and right, that's a different issue. Okay? Perhaps. And then there are a couple other ideal cases. The funnel and the smiley face, or whatever you want to call it. Okay, well, there's a pattern of residuals. Positive, negative, positive. Okay. So in parts, in these two pictures here where you have the funnel or the double bow, some kind of transformation method will usually correct that. In other words, you can correct the non-equal variance assumption by transforming, let's say, the y variable. Take a square root transformation or something. And we're going to have some cases where, some special cases where you can actually do that. And then in this case where the residuals have a pattern, then clearly you're missing some kind of term in the model. You're missing a term in the model. All right. Maybe as the author suggests, perhaps a quadratic term. Right? In a simple case. So those are just some pictures to be aware of right now. That's about it for residuals. Any comments or questions? So it'll be part of your everyday calculation from now on. You'll have to make residual plots. You may not have to do it, like 40 pages of Excel for every problem, but you may want to do some calculations. Probably the normal probability plot is kind of down the list in terms of the things you really need to do. but it is something you will want to do occasionally. Okay. One last thing before we, well, maybe we should take a break now.
Good idea.
Okay. Then we'll talk about lack of fit. We're going to talk about lack of fit when we come back. All right.